In this last section for Unit 6, we're going to look at the properties of these compounds by type, both for the ionic and the covalent compounds. Covalent molecular compounds have physical characteristics that are unique to them, unlike the ionic we looked at earlier. These guys have low melting and boiling points, as opposed to ionic being very high. If you've ever made caramel for caramel apples, you know if you put sugar in the pan just on your stove top, you can start to melt that covalent compound, C6H12O6. So it doesn't take much, and then it'll boil and turn into caramel. Most are gases at room temperature, and if they're not gases, then just the surrounding energy can make them vaporize. Water is a covalent compound. You leave it on the counter, it will evaporate overnight. So it just took the energy from the air around it to go from a liquid state to a gas state. And at or near room temperature, most of them are soft. The word being malleable means you can squish it. Kind of like chewing gum's a solid, but it's soft, it's malleable. And there's a quick check. If you give 3 properties of the covalent compounds. So I have little blank boxes. If you can fill those in, that means you paid attention. If not, you probably should go back to the last slide and recheck. There's another characteristic called electronegativity. It's the strength of an atom that it has to attract the bonding pair to itself. So once it spin pairs and creates a bonding pair, a single bond with another atom, its electronegativity tells you how strong it is, where it's going to hold that pair closer to its center, or if the other one is. Chlorine, when it bonds to another chlorine atom, diatomic, the shared pair are equidistant from the 2 centers. And that's because the density that comprises that bond is then located halfway between the 2. One chlorine atom will not hold that pair closer to itself than the other. Remember, it's the big protons in the middle of each atom that are pulling on those electrons, trying to reach stability. In this case, diatomics, they hold it equally apart. So here's chlorine. There's the bonded pair right here. That bonded pair is equal distance to the red chlorine as it is the blue. So nobody has an advantage. But what happens when the 2 atoms aren't the same type? Each has a positively charged nucleus that has different attractive forces depending on who has more protons. So they pull an electron pair, the spin paired electrons, to different amounts or different degrees. The end result is that bonded pair is shifting towards one of the 2 bonded atoms, with the one that has the higher electronegativity, the one that has more protons in the middle to pull on those negative electrons. We like to use HCl, hydrochloric, hydrogen monochloride. So there's the bonding pair of the little box when these 2 spin paired up. But because chlorine has more protons, it has a higher electronegativity, it'll pull those bonded pair closer to its center. Result is that hydrogen no longer is neutral. It has a slight positive charge, kind of like the North Pole on a battery, the plus on a battery. This little funny little Greek symbol means that it has a slight charge and it's positive. Where chlorine, since it's holding these negative electrons closer, is slightly negative charge because it feels those electrons closer. Attracting electrons are electronegativities. The larger the value of the electronegativity, the greater that atom has the ability to take that bonding pair and attract it to its center. And this is a little 3D diagram where we're going to look at the same compound so you can see how this thing's red. And you have that table in your resources section. So there's good old HCl. There's hydrogen. And there's chlorine. If you look at height of those boxes, you'll see that chlorine has a higher electronegativity, 3.0, where hydrogen, normally over here above lithium, is treated like a nonmetal in this case. And it's over there. Its electronegativity is less. There's hydrogens, and there's chlorines. So what happens to the bonding pairs? If they're held equally, like the first one with the two chlorines, we call that a nonpolar covalent bond. One is not holding it closer to itself than the other. So it's not slightly more negative than the other being more positive. They have equal strength, if you will. Neither one sees the electron pair any more than the other one does. So there is no pole difference. You can also have a nonpolar covalent bond anytime the two atoms involved are the same, like I said, the pair of chlorines, or if the difference between the electronegativities is really, really small, then it'll act like a nonpolar. We consider it nonpolar. That's the tricky part in this section. So again, back to hydrogen chloride. If we look back on that table, we'd see that hydrogen had electronegativity of 2.1, while chlorine was 3.0. So chlorine being higher than the other is going to want to pull it closer. But now we can also have a bond where the electron pair is shifted towards the one atom, and that's called a polar covalent bond, kind of like we just saw with HCl. Since it's shifted, we now have a poles. We have a plus and a minus, a north pole and a south pole, like a battery. And so they'll be pulled closer. Atom that has more strongly attracts the bonding pair is slightly more negative, just like we saw before. And the one that can't hold it as close is more positive. And the larger the difference, the more negative and positive the atoms become. In fact, it's a way we can actually predict the type of bond that will form between two elements. And here's a table. If those two you take the electronegativities of the two, if there's a difference between 0.0 and 0.2, we call that a nonpolar covalent bond. There's just not a big enough difference where we see this north and south pole, this plus or minus. It's the weakest bond in terms of strength, and it's the least stable. It's easy to break them apart. If it's 0.3 to 1.4, and again, this table will be available for you for tests. Now the difference is getting big enough, we call it polar covalent, and it has a moderate bond strength, and therefore it's moderately stable. So that's our table I just showed you on the other page. So back to our little, in this case, hydrogen, but chlorine, the same thing. They're both the same. So hydrogen has electronegativity of 2.1. So does the other one. Their difference is 0, so it's nonpolar. Back to our little HCl. In this case, this is hydrogen fluoride, same idea. Hydrogen 2.1 on our table. It shows fluorine, but chlorine, fluorine's even higher. Chlorine 3.0. 3.0 minus 2.1 is 0.9. We look at our little table up here. That's between here. We said that's a polar covalent compound. So it's moderately strong. Back to characteristics. Ionic compounds, they form crystals of repeating patterns. This we learned back in 6.1. And when they do, their crystal lattice is a three-dimensional arrangement of particles, just like the little red and white model that I have sitting on my table that you've seen before. These guys are hard, rigid, brittle. They have very high melting points and boiling points, unlike the covalent, which is low. They conduct electricity when you melt them or dissolve them in water. It's called an electrolyte. It's hard to break because these bonds are very strong. When they do, they give off endothermic reactions. they absorb energy. Endo means like into. So the reactants plus energy will produce products. So sodium plus chlorine, when you put them together, form sodium chloride. It actually gets cold when they do it. Bonds are broken. You get ice packs. That's why it feels colder to you when you break them. Photosynthesis. It's actually cooler in a forest. Versus exothermic reactions where they release. Exo means coming out. The thermic or the energy is coming out. In that case, the reactants in these, when they break them apart, produce product and an energy release. In this case, bonds are formed. You're putting things together. Heat packs are like that. When you crack them and put them on, it feels warm to you because now you're creating a new product inside that pouch. In the process, it's forming bonds and releasing energy as it does so. Combustion is a form. We burn our Bunsen burners. That is an exothermic reaction. You're producing carbon dioxide and water. You should be able to come up with 5 properties of ionic compounds from that long list. Usually these are open response questions on a test where you have to list them. So have an idea of which are your favorite. Then we're going to last look at the case where 2 atoms have extremely different electronegativities. Again, we'll use sodium chloride. It's ionically bonded, and that's because electrons transferred from the metal sodium to the nonmetal chlorine. So if you look at our periodic table, sodium has an electronegativity of 0.9, and chlorine, as we've seen before, is 3.0. Well, 3.0 minus 0.9 is 2.1. And for ionic, the last one we say anything above 1.5 or above is ionic. It's the strongest bond, it's the most stable. Well, instead of holding them closer like in polar covalent, ionic, it rips them off. Literally and figuratively. So 3.0 minus 0.9 is 2.1. That's definitely ionic.